Hi everyone, welcome back to the Reading Club. This is an ongoing series where I read papers on mixed integer programming and discuss their key ideas in simple language. And in today's episode, we are going to continue covering this paper, Symmetry in Integer Linear Programming by Francois Margot. And this is the fourth part. If you haven't seen the first three parts, the links will be in the description below. And in today's episode, we are going to look at pruning the search tree based using this kind of symmetry relations in integer linear programming. Okay, so recall that we represent our symmetries in permutations, right? So let's say if we have this kind of a permutation, which is 3, 2, 1, 4, which basically means that one variable number 1 is symmetric to variable number 3, 2 is symmetric to itself, 3 is symmetric to 1, and 4 is symmetric to itself, right? And this set of permutations basically form a group which has its own properties, right? So all the algebraic group related properties we enjoy. Now the question is that can we use this kind of symmetric groups or symmetric permutations to prune the search tree, right? So we have our search tree where we at each node we solve linear relaxation and make branching decisions and split the search space into two parts or sometimes even more than two parts. It depends on the solver. Okay, so let's say we are somewhere over here and there is still a lot to explore under this node. Okay, so there is still a lot of nodes maybe there and we still haven't reached our final answer over here. Now the question is that can we avoid exploring this based on symmetries, right? So when can we avoid exploring the part of the search tree is if we know that first of all that this subtree does not contain any feasible solution, then obviously yes. If we know that this subtree contains feasible solutions, bunch of solutions, but none of them are optimal solutions, then of course again yes, that's the basic pruning that we use. It's in the branch and bound tree search, right? And the third one is that if we know that there is an optimal solution over here, but its symmetric solution will be present in the rest of the tree, somewhere in this part of the tree, right? So all these nodes, children, if we start exploring, then one of its symmetric optimal solution will be present in this part of the tree. If we know this for sure, then definitely we can avoid exploring this tree. So this is what we are trying to do. Okay, so how can we do that? Okay, so this is based on we are going to look at domain based comparisons. Okay, so if you let me write down some variables 3 4, and let's say that this is the node A and the domain that we have at node A is something like this, right? So let's say if this one has 1 2, this one has let's say 2 3 4, this domain has let's say I don't know, let's call it 3, and this one has 4 and 5, let's say, right? So this is like the domain of integer values that these variables can take. Okay, now let's consider this node B over here. Okay, so note that the B is not the parent of the A. That's how I'm picking the node. Any node that is not basically a parent of this node A, right? So what we are trying to do is we are trying to compare the domains of these variables under node A and node B. Okay, so let's say what these domains would be. So first of all, there will be no directly inclusions in this kind of domains, right? So domain A will never be completely a subset of domain B, right? Because essentially they don't have the same. Essentially, we branched on some node to split into two nodes, and they are basically in different branches. That basically means that some variable will have to take values that are not included in the domain, right? So the domains are completely split in at for some variable, right? So for example, over here, the domain of the first variable might be, let's say, 3 4. Okay, domain of two the other variables might be same, right? So let's say this is just 2 3 4. Let's say domain of 3 is I don't know, what should we have there? Let's say 1 2, maybe, I don't know. Yeah, it sounds like a decent domain. Okay, and domain of variable number 4, let's call it, let's have this one as, this one, let's say it's a subset, right? So let's say 4, 5, 6. Okay. So clearly these domains are not really comparable, right? So 2, 3, 4 is a subset of 2, 3, 4, 4, 5 is a subset of 4, 5, 6, but 3 and 1, 2 are, neither of them are subsets of each other, and 1, 2 and 3, 4 are also not subsets of each other. So there is nothing to compare here, right? So there is no this relationship, there is no this relationship, there is no equality, nothing is there between these two domains, right? So there are two different nodes. But if we look at this particular permutation, right? So 3, 2, 1, 4, which basically says that variable 1 is symmetric to variable 3. So if I compare the domain of variable number 1 to the domain of variable number 3 over here, right? So 1, 2 is a subset of 1, 2, right? 2 is symmetric to itself, so 2, 3, 4 is a subset of 2, 3, 4. 3 is symmetric to 1, so 3, if I compare it over here, so 3 is a subset of 3, 4, and 4, 5, that the variable number 4 is symmetric to itself. Its domain at node A is subset of domain of node B. Then basically we can say that domain of A, right, is a subset of a domain at B, but we have to actually permute the variables, right? So under G, if we do this, then we have this kind of inclusion relationship. So what does this mean is that whatever I end up exploring in node number A, right, its a symmetric part will be explored at node number B, at least that part, right? So if this one contains an optimal solution, then definitely there will be a symmetric optimal solution which will be explored at node number B. So if this happens, then we can safely prune this node number A, and we can, happily continue our search in the other parts of the tree, right? So of course, like how many nodes do we need to compare like this? So we definitely don't need to compare node A with every possible node. We can just compare this node A to the nodes which are in the immediate right in the path of the node A, right? So this is the path of the node A, right? So root node, and then this node, and then this node, and this node, and anything that is immediately to the other side, right? This node, and this node. This basically it's sufficient to explore only these things, right? Because the domain of domains over here are already a subset of domains over here, so we don't really need to compare with domains over here or here or things like that, right? So this is a simplest way in which we can use symmetry to prune our search tree. So the question is now, can we do something smarter than that basic level of pruning, right? So the answer is yes, we can, but the math little bit gets complicated, okay? So we have our permutations G that represent symmetry, and these symmetric permutations are part of a group called G, right? And for every group, we saw that in the last part that we have something called fundamental region. Fundamental region. Right. So I'll just briefly describe if you haven't, if you don't remember it from the previous part. So that it's basically, this is like say the entire search space. Then we have this small fundamental region which contains a small set of points from our feasible region, and it guarantees that it has the optimal solution, right? At least one optimal solution under the symmetries that we consider for this particular problem. Okay. So the goal is that we only want to explore this small set of points instead of exploring the entire space. Now, the way we discuss the fundamental region, the way we find this fundamental region is, so we discussed like one possible way, right? So it was basically that we find a point x bar somewhere in the plane, somewhere in the hyperspace, and then we take the image of x bar, g of x bar minus x bar, and then we make a dot product with a point, let's say z, and if this is less than or equal to 0, then we know that z belongs to the fundamental region. Okay, so this is a fixed point that we picked, and it has certain properties, again like all those things we discussed in the previous part, but it's, as of now it's not important. So this is a fixed point, and if we do this kind of things, then if a point z satisfies this inequality, then it belongs to the fundamental region. Now let's, and this has to be true for all G in my group. all the permutations in my group, this inequality has to be true for that particular point Z. Okay. Now we can basically write it in a different way, right? So let me write it as g of x bar dot z is less than equal to x bar dot z, and this has to be true for all g. And instead of writing it like this, I'll say that, take the maximum of all of this under all g belongs to g. Okay. So if we do this, then it's basically the same way of writing this thing. Okay, these two are equivalent. And now let's actually consider a particular example. Let's say if my x bar is 1, 2, 3. Okay, and let's say I pick the permutation g, under which the image of x bar looks something like, let's say 3, 1, 2. Okay, and let's also have our z, right? So let's call it z1, z2, and z3, right? So what would be the left part of this inequality? It's 3 times z1 plus z2 and plus 2 z3. Right? So this is the left part. I'm going to ignore the right part for the moment. But let's try to see what the left part is, which is in this case for this particular permutation g, it looks something like this. Okay, so if I multiply g of x bar times z, and then we get this. But we can get it in a different way also, right? So now we permuted the indices like the elements of x bar, but we can also permute the elements of z, right? So let's say I pick the inverse permutation g inverse of z. So then how does that look like, right? So here the element 1 went from position 1 to 2. So position 2 has to go from 2 to 1. So this first element will be z2. The second element will be, so 2 went from 2 to 3. So 3 has to go from 3 to 2, right? So second element will be z3 and the last element will be z1. Okay. So this is z2, z3, z1. And if I multiply g inverse of z to x bar, I get the same thing, right? So this is z2 times 1. So z2, z3 times 2. So 2 times z3, and z1 times 3. So 3 times z1, right? So it's basically the same expression that I get if I apply g inverse to z and multiply it with x bar. So essentially what I can do is I can rewrite this expression in this way, that max overall g in my group g, right? But instead of taking an image of x bar under g, I'll take x bar as it is, and I'll take the image of g inverse, image of z under g inverse. Okay, so this should be less than equal to x bar z, right? And since I'm considering all elements in the group, right? So since this is a first of all algebraic group, its inverse also belongs to the group, right? So this is also in the group, right? So g is in the group, then g inverse is also in the group. So if I'm going to iterate through all elements of this group, then I don't really need to take the inverse. I can just keep the elements as it is, right? So eventually I'll consider both inverse and its original element as well, right? So g and g inverse will both be considered over here if I consider g inverse, or if I don't consider g inverse and keep it g itself. Okay, so now this tells us something, right? So this expression is, it says that z, so if this is satisfied, then we know that z is in the fundamental region, right? And we can just explore only those points. So for z to be a fundamental region, it has to be, according to this, lexicographically maximum, lex max, under this operation, right? So if I multiply it with x bar and take the permutations with permutations of its indices under this set of permutations, then this particular point is the maximum of all of that, right? So the z is basically the lexicographically maximum point in under this kind of an operation. So we are going to use this to prune our search tree. So let's see how we can do that. Okay, so far we know that if Z is the lexicographically max element, then it belongs to our fundamental region and we need to explore it. And if Z is not the lexicographically largest element under that operation, then it does not belong to the fundamental region and we can skip it, right? Now, the problem is that Z is a fixed point and we can easily obviously compare whether it's a lexicographically maximum under a set of permutations or not. But at our nodes, we don't have fixed points, right? So we have domains. Basically, we have for variable 1, we have a bunch of possible values. We have variable 2, we have a bunch of possible values, and so on and so forth, right? So what we need to do is we need to compare these domains with another set of domains, right? So that we can say that, some sort of lexicographical relationship between set of domains, right? So if we have that, then we might be able to use that to figure it out whether the lexicographically largest element will be there in this node or not, right? So that's the idea. So what we are going to do here, we are going to compare another domain here, and here we are going to compare keep the smallest element on this side, and we are going to compare that smallest element to the largest element on this side. Okay, so the smallest element on this side, let's say it is this one. I'm going to compare it with the largest element on this side, which is this one, let's say, right? And so on and so forth with all of them, right? So this is the smallest element on this variable 2's domain. This is the largest element on variable 2's domain over here, and we compare, right? So we keep doing this kind of comparison. So as long as we have equality between the smallest and largest, we move on to the next one. If we have equality, move on to the next one. As soon as we hit one inequality, we can discuss. We can basically declare that one domain is lexicographically larger than the other one. To be precise, like this domain is lexicographically larger than this domain, right? So in fact, all the points on this domain, we can say that will be lexicographically larger than all the points on this domain, right? So if we have this kind of a node, then we know that a point over here on this node will never be lexicographically larger if this domain is a permutation of this domain, right? So that's the key idea. So let's actually try to understand it with an example, right? So it becomes easier to understand. Let's say if we have variable 1, 2, 3, 4, and let's say we have the domains like this, right? So let's say we have domain at node B and domain at node A. Okay, so domain at node B are 1, 1, 0, and 0, 1. Okay, and domain at node A are 0, 1, 0, 1, and 1. Okay, so we are going to compare the smallest element on this side, which is 1, the largest element on this side, which is 1. So these are equal. Here the smallest element is 1 and the largest element here is 0. So this is clearly an inequality over here. So we don't really need to compare anything below over here. As soon as we find one inequality, we are kind of done. So domain of B is lexicographically larger than domain of A. Now here is the interesting part. Okay, so if I consider the permutation 3, 4, 2, 1, if this is the symmetric permutation for this problem, in that case these two domains are actually equal, right? So if I permute consider this permutation, so compare element number 1 to element number 3, 2 to 4, number 3 to 2, which is here, and the 4, which is 0, 1 here, and 2, 1 to 0, 1 over here, right? So in other words, what this is doing is saying that a permutation G of domain of A is equal to dB, which we said that it is lexicographically larger than dA, right? So we already find one permutation under which we have the domains which is strictly larger than lexicographically larger than this domain, the original domain, right? So if I consider all solutions of the node over here, and if I apply this permutation, then the permuted elements will all be lexicographically larger than these points, right? So all of these points will be lexicographically larger than all of these points, which basically means that node A, this particular node, will never contain the lexicographically largest element in my solution, which basically is in the fundamental region. So we can basically, none of these points are in the fundamental region, and we can basically remove this entire subtree over here. We can basically prune this subtree at under the node A, right? So that's the key idea behind the pruning, and it is far more stronger than the pruning that we considered first, right? So which basically compared two nodes, one node here and one node here, and then we compared domains of this node with permutations of domain, and it needed to be like this kind of an inclusion, not necessarily a lexicographical relationship, right? So this is a lot weaker than this condition, right? So this condition, first of all, a domain at any node, we are basically not even comparing with domain at other nodes. We are comparing it with itself under different permutations, right? And even if I don't even know the domains at the other nodes, I can still prune this element, because based on the arguments about whether the points on this, the feasible solutions on this side will be in the fundamental region or not, right? So that's amazing. That's basically all the things that they have discussed in the pruning section. Okay, so to conclude, we discussed two methods in which we can prune a particular node in our search tree, right? So the first method is we look at the domains of element of the variables under that node, and we look at the domains of those variables for a different node under some permutation. If it happens that there is a subset relationship like this, in that case we can prune node A, right? Or the other case in which we have the domains which is under some permutation is lexicographically smaller than itself. In that case also we can prune this node A again, right? So these are the two ways in which we discuss. So this one actually involves a little bit of math to understand why this is valid, but this is trivially obvious, right? So, but again, like if it is obvious, but at the same time it is not super frequent because this does not happen very frequently, whereas this happens quite a lot. Okay, so these are the nice two ways in which we can use symmetry to reduce the size of the search tree, and basically we can explore less and finish our search quicker, right? So I hope you learned something new from this. I'm not really going to cover other topics from in symmetry. So this is basically the last part for this particular paper. I might consider other papers later on, but this is pretty much all for now under for symmetries in integer linear programs. So hope you liked it, and see you in the next episode. Bye.